My name is Peyton Chandarana. So I'm part of the ICAS lab under Dr. Zan. I'm working towards my PhD. There we go. Nice. Right on time. So I am a PhD student. I did my undergrad here in computer engineering. So I've been here for a while. I've been here since 2015. So it's been a while. So now I just decided to go ahead and do my PhD because I like neuromorphic computing. I took the course 2 years ago. So I just kind of fell in love with neuromorphic computing mainly because it's very biologically inspired. Having biology and computing kind of intermingle with themselves is something of a lot of interest to me. So I kind of like to do both of the sides. I was in Dr. Valifar's lab for a little while, did with computational biology and stuff for a little while. Then I said, okay, well, neuromorphic computing sounds nice. I'll take that. And so here I am. I'm going to be kind of presenting kind of like the basis of conversion tools in neuromorphic computing. I'll kind of explain why they're conversion tools and why they're starting to kind of phase out a little bit. I'm going to be presenting one of the works which you'll actually use in your third assignment, right? The second one's encoding though, right?
So they didn't have the first assignment in this. They had it last year. But now this is going to be the second, and they're going to have the third assignment later.
Okay. So yeah, your encoding assignment, I'm not really going to go into depth too much with it because it's basically just read a paper, implement some encoding, decoding algorithms. So it should be fairly straightforward. But today I'm going to kind of present the paper or the assignment that you'll have afterwards, which will be actually creating a neural network in TensorFlow or PyTorch, whatever you choose, and then converting it to a spiking neural network. Like I said, this paper right here, this person, Rueckauer, his first name's Bodo, he developed this SNN Conversion Toolbox, which kind of became the mainstream conversion method. But again, it's kind of falling out of favor lately. Okay, so first I'll kind of start with a basic spiking neural network intro. Then I'll kind of give you a detailed overlook into the SNN Toolbox or SNN Conversion Toolbox. They're the same thing. Kind of give you a big overview of that, why it does certain things, why they even exist and whatnot. And then I'll give you kind of a demo on what you can expect for the next assignment. So you've got one that was, I think, assigned to you last week, but after that one, this is where this upcoming assignment will come in handy. Okay, so a quick review, kind of. I know Dr. Zan, last semester when I was doing this presentation, they hadn't really gotten to the point of spiking neural networks, so I'm going to just go over a quick review with this. So Dr. Zan's gone over what a spiking neuron does. So you have some kind of voltage. And the way this voltage happens biologically is you have what's called ion channels. So these ion channels are basically little doorways into your neurons. And basically, if you know about chemistry, you have some positively charged ions and negatively charged ions. So your neurons are constantly fighting a battle of hyperpolarizing, depolarizing, equalizing, and whatnot. So these flows of these ions go in and out of the cell very quickly, which ultimately causes what's called a action potential or spike. So the basis of spiking neural networks. You have the neuron, which is you can think of as the whole neuron. Yeah, did you have a question?
So yeah, is this like the actual brain synapse firing?
What, this right here?
Yeah.
This is the behavior, yes. So this is kind of what it looks like. When you have an influx of sodium ions, you get a huge increase in voltage or membrane potential. And then it releases potassium ions, which causes what's a repolarization, which goes all the way down. It actually dips below where it was at baseline or resting. This is what the actual biological spike looks like. Now you have other chemicals and everything that cause different behaviors and stuff too, but this is in general how a spike kind of looks. How ions come in and then go out and cause that membrane potential. influx or fluctuation.
Just add one small thing, and everything says fine. It's correct actually, but like this is not a CNN. There's no.
Yeah.
We talked about it, right? So the Hodgkin models and everything. That is what it is.
Yeah.
CNN is a little bit different.
So one thing I want to mention here while I'm here, the way they perform this test, how they got this graph, is you've got your neuron body called the soma, and basically they took a little probe or pipette and attached it to the body of the neuron cell, and they basically injected or took out fluids, which basically simulates the influx of the different ions and whatnot. It's called patch clamp. So yeah. So this is how they got this graph originally. So at the end of the synapse, it looks like zeros or ones, and what's actually happening at the end of the synapse is more of a release of chemicals into the next neuron. Okay. Anyway, that's enough about neuroscience. So the base thing I want you to get from this is obviously just biological bits, zeros and ones, that are being transmitted from neuron to neuron. And then, so these, like I said, these bits are called spikes in action potentials, just fluctuation of currents in the cell. And then how this information is encoded, how it actually represents something other than just zeros and ones, is either in the spike rate, so how many spikes you have in a finite amount of time, or the temporal pattern between the spikes. So you have this amount of time between these two spikes and whatnot. That's how data is encoded in the brain as well as spiking neural networks. And this all is kind of at a higher level view is event-driven computation. Somebody, you've never seen an apple before, you don't know what an apple is. If they just hold it behind your head and say it's an apple, you don't know what it is because you haven't had that stimulus yet. So our brain is always working off of event-driven or stimulus that's coming in. Okay, so yeah, I think you've probably seen this, how this kind of works with the neuron cell. You have this part right here, it's called the soma. Then you have your input dendrites right here. Then you have a long axon. And then at the very tip right here of the neuron where it connects to another neuron as input, that's your synapse. So this axon is one thing that spiking neural networks doesn't necessarily simulate. This axon has its own certain behaviors and characteristics as well. But spiking neural networks, at least the ones that are trying to relate back to artificial neural networks, don't take this into account. So, okay, so yeah, so you either have two types of encoding. You either have rate-based encoding or what's called temporal encoding. Rate-based just encodes information in the rate or the frequency of the spikes. Temporal is in the time between the spikes. Yeah, so actually your assignment that was given to you last week will be creating some temporal encoding mechanisms. There's, I think, 3 or 4 of them that you have to implement. There's step forward, threshold-based representation, and moving window. And then you can create your own. The neuromorphic community, kind of like I said in the assignment write-up, is always looking for new encoding algorithms and decoding, which is actually what my project was about in the class. Okay, so without further ado, here's the toolbox. So I didn't make this. This is somebody, like I said, R. Bodo made it. So he made it back in 2017, kind of benchmarked it and everything like that before Loihi Intel neuromorphic processor came along. So, okay. So what's the purpose of converting? So you're just obviously converting from an ANN to an SNN. So first you have to develop an artificial neural network or a deep neural network. And then once you've trained it, once you've stored the weights, once you've tested it, make sure the accuracy is up to par, that's when you convert it to a spiking neural network. So if you're wondering, okay, why don't we just make a spiking neural network from scratch? It's hard. You have to have a lot of background in neuroscience to build one from scratch. Not only is it hard to build the actual spiking neural network, to do something end to end, training it is another issue. So Dr. Zanz mentioned the non-differentiability of spiking neural networks because of their discrete nature. training it is another whole issue, right? We have backprop in ANNs. We don't have backprop here. Well, we can have it. We just have to add some stuff to it. And then, yeah, so like I said, design and training is active area of research. Things are constantly going on. So lots of hyperparameters too. That's why it's hard to design one. You have, in addition to the weights and activations and the biases that you're used to with ANNs, you have membrane potentials. If you're doing Hodgkin-Huxley, you have to take into account like ion channel behavior. It gets to a lot of hyperparameters to do. And I mean, you have other things like if you're actually trying to mimic the brain in a spiking neural network, you have to do inhibitory and excitatory kind of layers and whatnot. Anyway, so point is they're somewhat hard to build from scratch. Most of them end up being just MLPs. You can build convolutional spiking neural networks, but there's some, you either have to use backprop to train them, or you have to somehow get the weights and convert them or something. So, yeah. Okay, so why does this specific work exist? So this Bodo, the Rueckauer Bodo guy, saw that all the other conversion methods were kind of one and done kind of thing. So they built an MLP, or they built a CNN, or they built an RNN, and decided, okay, that's all I'm going to build. I'm not going to actually go make it more general. So he developed a tool that allows you to kind of just take an ANN and do the same thing as spiking. So he mapped all the different layers, most of them, to spiking neural network domain. So all this SNN Toolbox is just a package you use from Python. You can just install it. It's available. I will say this repo is not being managed anymore, so it's kind of out of date, but it still does work. I tested it today. So you have to install this SNN Toolbox. I'll show you how, or maybe not how, but how to import the environment that I give you. So yeah. Takes convolution layer from ANN, has an equivalent spiking version. So he's kind of built out the different layers for you so they're easily available to just map one-to-one for the most part. But there are a couple things that do not exist in this conversion toolbox, which we'll see in a second. All right, so all this conversion is doing at its like core is approximating ANNs. So when you get that high accuracy in your ANN, you can reasonably assume you're only gonna be able to get up to that accuracy or lower. So your ANN training accuracy is most likely gonna be an upper bound on your accuracy or performance of your network. This is because, again, we're approximating the ANN in the spiking domain. We're not actually creating it from scratch, training it from scratch to take the benefits of spiking neural networks. All right, so first thing you got to do, create your ANN. So I think in the next assignment, it'll be VGG 16 or something like that, or VGG 11, and you'll create that ANN, you'll train it on CFAR 10, and then once you're done training with TensorFlow or PyTorch, whatever you choose, you save the trained networks with the weights and activations, and then you convert the weights and activations to the spiking domain. So basically, he's built a parser. It parses your network from your weights and activations, and then imports that into his model or his software and makes you a new neural network. Yeah.
So basically, you train regular network and then just convert it into
yes.
spiking.
Yep. So the spiking neural network actually kind of approximates the regular neural network, the ANN. Okay. So here's kind of some details. And so you can read this paper down here and figure out more about the conversion process in detail. But here's a high-level view. The first thing that happens is that your images are encoded to spike rates or currents. So instead of doing spike rates, you can actually do just currents, regular old DC currents into the SNN. And from there, those currents go into your first layer and actually start activating the neurons and whatnot. All right? So then from there, activations are converted into spike rates. So your activations output a rate of spikes as well. And then your biases are converted with constant currents, clamped to spiky neurons, whatnot. So you've got all these different pre-processing steps that happen to kind of convert and match, kind of do scaling, weight normalization, all kinds of different things that are going on behind the hood. So yeah, database weight normalization, it should be a T right here. Basically, they explain this in the paper. When you're converting these ANNs to SNNs, a lot of previous works were saying, okay, we're going to take the highest activation and normalize all the activations and weights based off of those. But what Araboto does is he actually gets the 99th percentile of the activations values and sets that as the normalizing parameter. And the reason he does this is to prevent what's called the dead neuron problem. So in spiky neural networks, unlike ANNs, you can encounter where you have a very high activation, and then for one test case or test sample from the input, and then if you normalize off the maximum, off that maximum, then there's a possibility you'll never reach that activation to actually make the next neuron fire. So yeah, if your neuron doesn't fire, then it's dead, right? Yeah.
Is that just the SNN version of like overfitting then?
Yeah, kind of, because you have a specific test case where you're putting in an image and your network basically, because it's normalized to the highest point or the highest activation, you never reach that point to actually fire anymore. So it's fitting to that one data point. Yep. So what are the advantages of this conversion process? Well, it's easy. That's for one. We got to a point in spiky neural networks where we're like, oh, we don't know how to train it. We don't know how to do STDP. We can't do STDP on really deep networks and whatnot like that. Which, Dr. Zan, have you gone over learning at all?
Not yet, no.
Okay. So STDP is a learning algorithm for kind of adjusting weights and everything inside of spiky neural networks, which you'll learn later. But STDP is not very good for really deep networks. There are different renditions of STDP that kind of hope to solve some of this, but for the most part, it's not very good with deep networks. So obviously, there's much less of a learning curve. You don't have to worry about every single neuron in your and tuning each and every neuron and its threshold and the input and the weights and everything like that. You don't have to worry about that with conversion. You can just do one-to-one conversion. Accuracies get close to state-of-the-art. So again, I mentioned that you have an ANN, that's going to be an upper bound on accuracy most of the time. Now, there are cases where accuracy sometimes does marginally exceed ANNs. And that's because spiky neural networks kind of introduce some noise, some stochasticity into the network.
What is SOTA?
State-of-the-art. Yep. So, but even though you might get a little bit of drop in accuracy, you're getting the power benefits, the energy benefits, and in some cases, latency benefits out of using spiky neural networks and hardware that's built for them. So like Loihi will have, I think I was looking at our results today, it was like 50 milliwatts consumption on something like VGG9, whereas something like a GPU or even just a like edge device, neural network accelerator will take 1 or 2 watts, right? So you get about 1,000 times difference in energy efficiency and/or, well, not energy efficient, but power efficiency. Okay, so, all right, so it gives us a baseline accuracy power, but yeah, but it's not ideal. So here's where the disadvantages of this conversion process come in. Again, when you do this, it's an easy way out kind of thing. So the first limitation that you have is not all layers are supported. So depending on what framework you use, Keras, PyTorch, or whatnot, can depend on whether or not it can be converted one-to-one. The other issue here is what simulator or what hardware you're trying to deploy to. So on Loihi, you can't do max pooling. So up here, if you look over here, max pooling is unchecked. So you can't do max pooling at all on Loihi and or any of these other simulators. Max pooling is something that this paper helped tried to kind of introduce to actually make this tool much more usable and help you get better accuracies with your networks. But this is a software-specific implementation. It's not hardware, or it hasn't been implemented on hardware yet. Okay, so rate-based encoding is not optimal. So at the beginning, when you pass the image in, it converts it to spike trains or DC currents. This causes a lot of overhead because you're constantly feeding in input and stimulus at a certain frequency. But this is not ideal because you could just encode it temporally. So you're introducing a ton of latency. You're introducing a lot of power overhead because each time you hit a spike, the more spikes you have, the more computation is going on. All right, and then you have less granular control.
Some of the output models don't support softmax activation. So like, or if we have multi-class classification, so we cannot use those models.
Multi-class classification? You can use ReLU. We've done that several times as well. Or have we? Maybe not. Let's see. PyNN, Brian2, and Megasim don't support it.
Yeah, I think what you can do, there was a student last time that were working with facial expression stuff. You can actually read the output of the layers and work with them. So you don't really have to have an activation function in the last layer if you want to do some kind of regression or something like that. You just directly read the output of that, just don't have any softmax or classification methods.
Yeah, and it was actually interesting when I was reading the paper today. There were 3 ways that they were proposing softmax can be done. There were 2 ways that involve looking at the membrane potential of the last layer. You just do softmax on that rather than the spikes and whatnot. And this may be an implementation limitation. Maybe he didn't have time to do it. Maybe these simulators like PyNN, Brian2, Megasim don't support this, which is my best inference. But this AnySim is built in. So this is his simulator. So when you're doing your homework, you don't have to have access to LeNet-5, but you can do everything in AnySim, which is included with the toolbox. Okay, so another disadvantage is less granular control. It's not like PyTorch, it's not like TensorFlow. You can't turn the knobs as much. You're converting a one-to-one network, a one-to-one translation. You're not going to have as much neuron by neuron control. And lastly, like I said, this was a thing that they developed to actually solve a problem that's temporary. So we're working on research solutions of how to do backprop on spiky neural networks, how to train them by hand, or like actually train SNNs. But conversions just was a temporary like plug and play solution so that you can get the power benefits, but again, not the ideal best performance you can get. So the biggest thing with these conversion methods is because they use that rate-based encoding, you get higher latency, much higher latency actually, because you have to wait for a period of time before all the spike trains can make it from end to end of the network until they propagate, feed forward through the network. So you have to have a little bit of overhead to wait for everything to pass through the networks. Okay, so I'll do a quick demo on how to do this. So this demo or this homework's not up, so because you're not on it yet, but this will come in handy in the future. So this homework will be posted as well later on, and you'll download it, and you'll have basically 2 different directories. You've got this assignments directory, which has that README file that tells you how to do the homework, and then you've got some tutorials to help you out. So I help give you the code that uses TensorFlow and stuff to actually help you avoid a lot of the hyperparameter tuning of just the ANN. Because this class is about neuromorphic computing, we don't want to spend all of our time on tuning the hyperparameters of ANNs. We just want to go with it. So in this tutorials directory, you've got 3 more directories. So the signals one is maybe one that you might use in this homework that you have right now. But for this next homework, you'll start with this model generator directory. So in here, there's just the source directory, And I think I included some sample output here. So if you want to use that and kind of make sure things are working as expected, you can use that. I highly encourage you using Conda or a pip environment or some kind of virtual Python environment, because there's a ton of dependencies. And you don't want to like overwrite all your system dependencies and cause a bunch of clashes. So I use Conda, and I included this ANN YAML file. And basically you just do conda env create -- name demo nc, and then do -- file ANN YAML. And this will retrieve all the dependencies for you. So you don't have to worry about installing package after package.
Can you do it on some cloud like Google Cloud or something like
Yeah,
that?
you could do that. That's this way too. You might have to install things a little bit differently. There might be a way I think pip can use the YAML file. But yeah, make sure it got everything. Resolve packages not found. Okay, might be because I'm on an ARM Mac. I tried it on my desktop or my laptop or my desktop, but yeah. Anyway, this will import the all the dependencies you need. From there, all you have to run is Python 3, and then just source LeNet.py. So this LeNet.py file has LeNet. It's a 5-layer network. It's got, I think in this case, it's 2 convolution layers and 3 dense layers. And basically, when you run this command, Python source LeNet.py, this will actually train your model. So you can tinker with this, you can change parameters, you can change the data set in here. So if we take a look at it. So it imports everything you need. It's got some global variables to help you keep track of some, like using a GPU or whatnot. It imports the data set, splits it up into test and train data, and then it just does a bunch of checking. So all this does is checks that certain files are there and whatnot. So you don't have to really modify much of this. And then checks if GPUs are available. If not, use the CPU to train. It's got some pre-processing, data set, convert to NumPy, just some data set manipulation. I know this looks like a lot of code. It's not that bad. Most of it you don't have to change. Really, the only part that in your assignment, after the one you're doing gets done, is you'll have to change the data set from MNIST to CFAR10. So instead of doing MNIST classification on handwritten digits, you'll go up to this top line, do a lot of scrolling. You change this DS name, data set name, to CFAR10. That basically tells the program, grab down CFAR10, and you're already training on CFAR10 using LeNet-5. From there, you'll have to actually change the network architecture, which is further down, a lot further down. What now?
Dimensions of the layers.
So I think my program handles this. I don't think you have to change anything, because I think, see, I have input image shape. My program actually looks at the data and reshapes it to the correct data set. So LeNet typically uses, I think, 32 by 32, but CFAR10 and, well, CFAR10 I think is 32 by 32, but MNIST is 28 by 28. So my program kind of handles this a little bit. So yeah, you have your 2 convolution 2D layers here with the kernels and average pooling layers between. And then you have 3 dense layers down here. 1, 2, 3. So there's your LeNet. And then we compile and train like normal.
I wanted to add that for those of you who actually have a project that involves creating your own model for different data sets, you can actually use this code for that as well.
Yeah.
You can just create your own code. If you're not familiar, if you're already familiar with TensorFlow or PyTorch, good. But if you're not, you can see samples of the layers here. Then you can just add or remove layers in case. Actually, when you do VDG, later, do we show them VDG or
No, we let that. That's the whole assignment is doing.
So with that, actually, that's a good thing about assignment that you learn how to add more layers to it. But pretty much, your project, if you have a project that involves CNN, which I think most of you do, you just need to change this part of the code and the data set.
So, did you have a question? Yeah.
I was gonna ask, can we add layers?
Yeah.
Is that one? Okay.
Yeah. So you can go in here and I could like, if I wanted to make this LeNet-6 or something, I could take and add a convolution 2D right here before this flatten layer. So you can tweak it as much, and that's kind of what VGG does. It has certain VGG blocks where you have like 2 convolution layers and then a pooling layer and batch normalization. Then you go to the next one, couple of convolution, and between those 2 convolutions, you don't have any kind of pooling. So that's actually part of this assignment is you'll actually create VGG9 or VGG11, and you'll change the data set to CFAR10, you'll train it, and then you'll convert it, which those are probably going to be split into 2 different homeworks. So, but yeah, the first part of this is just change the network, change the data set, train it, get some accuracies. Yeah?
Can I add something here? So we cannot add a lot of convolutional layers since you are using just set2 by set2 images. So whenever that you add a lot of convolutional layers, you have, as Peyton mentioned, you have to use pooling layers as well. So it decreases the dimensionality of your images. So you cannot go down to, at some point you just have one by one feature maps, you know?
Yep.
So you cannot add a lot of
Poolings.
poolings.
Yeah, so basically every time you do a pooling layer, it reduces the dimensionality, and so you can't go below 1, right? The lowest you can go is 1. And TensorFlow will tell you. TensorFlow will yell at you and say, hey, too many pooling layers, this size is not sufficient enough to continue. So yeah, you create the model, you initialize it, specify your loss function, your optimizer, print the model summary, and then you start training. So this is TensorFlow. Like I said, if you want to use PyTorch, I haven't tested it on PyTorch, but I did test this morning and it does work. So use what you would like, but you're responsible for getting it working on PyTorch if you want to. Maybe I'll create a PyTorch example for next semester or next year. So we have a little bit more diversity. So yeah, you can just kind of plug and chug. Like I said, you just have to change the dataset name, it downloads it, deals with most of the shaping stuff, and then you change the network. Yeah.
How long did you take to train?
Oh, not long at all. If I had the dependencies on my Mac, if I could download them, then I'd do like 3 epochs, and then it's like 98% on MNIST. It's just LeNet-5. LeNet-5 is a really easy problem. Now CFAR10, the one that you're doing, might have to take longer to get a good accuracy. And I think what was it, Mohammed Reza, like 80% was kind of the highest we saw last semester on CFAR10 with the VGG network that we were using. It was 80 to 90%,
Yeah.
somewhere around there.
You should get for VGG 11, you should be able to get up to 93%.
Yeah.
But then you need all the stuff. So, but the accuracy doesn't matter.
Yeah.
So if you get to 89, 90%.
As long as your network's not guessing and or yeah, if it's not failing completely, then you're probably
It
okay.
wasn't-
Yeah. So I mean, I think you should be reasonably able to get above 70% pretty easily. So just adding a couple layers and whatnot. But yeah, we'll kind of give you an architecture to kind of go look at and develop it. We'll tell you VGG11, this here, you can go to this link. This defines the architecture so that you can implement it. And it's pretty easy to plug in new layers and whatnot. Okay, so that's the LeNet one. So after you train your LeNet, you're going to get a couple directories. You're going to get a data directory, which has NumPy zipped format like data of your train, test, and validation. It'll be in a data directory. If I could run it on my Mac, I would. So you'll get a data directory, and then you'll also get a models directory. And those 2 directories, what you'll do is you'll copy them to the SNN Toolbox directory. So you go in here, and basically you just have to put those in, and then you're ready to go, ready to start conversion. So inside of this SNN Toolbox directory, you have this SNN Toolbox.py, and I also included a YAML file again to help define the dependencies, so you can use that. Okay, so in here, this is the big one from SNN Toolbox import, the run or the main function. So in here, this is where we're actually going to do our conversion. And we're only, because not all of you can have access to Loihi and we can't give it to you, if you want to run something on Loihi, tell us. We'll help you run it. We'll have to run it for you and get the results. We'll try to work with you about that. But for the most part, you can do everything in their simulator. If you want to deploy it on Loihi, you have to keep max pooling out. You have to keep the average pooling layers only. And then what was the other constraint? There was another constraint for SNN Toolbox. I can't remember it off the top of my head. But yeah, max pooling is the big one. You have to have all average pooling if you want to run on Loihi. Anyway, so this basically is how you do the simulation. You have number of time steps per sample. So when I mentioned rate-based coding earlier, I mentioned that you have to expose an image for so long, or the spike train for so long to get it to go from the first layer to the output layer. So this is what this is doing. You're controlling how much the network sees one sample or one image. And if you have this significantly low, you'll get a terrible accuracy because your spike trains and the spikes that are formed from the input will never get to the end properly. But if you have too big, you'll probably get overfitting. So, but yeah, 18 is kind of sweet spot for LeNet-5 and MNIST. So that's pretty much where it needs to be. I think it's 95% accuracy, but you can increase it to, I think I tried 32 and you get like 98. So yeah, you can tweak this little parameter as much as you want to see how the longer you expose, the better the accuracy, the lower duration or num time steps per sample, the less accuracy you get. Then you have your batch size. So the simulator they have actually does support batch sizes. Loihi does not. It's one sample per batch. Then you have how many to test. So now we're done with training. We're not training anything here. So we're only testing things. So I set it at 100. You can set it to something else if you'd like. Just keep in mind with the toolbox, inference when you're recording like data takes a long time. So if you have 1,000 or 2,000 samples, then you're gonna have to wait for a long time for those images to actually do inference because it's also recording all the plotting data, the state variables and whatnot. Convert model true if you want to convert it. If you don't, then set it false. Then you have, it looks for your model inside of the models directory. And then it looks for your data inside of the data directory. Those two directories that I mentioned before. Yeah.
Sorry, just a random question. Would the number of test samples really have that much of an impact on the accuracies?
No. So I was just saying that it has an impact on which one? The num steps per sample?
No, the num test samples.
Oh, this doesn't affect accuracy at all.
Okay.
I mean, obviously you're going to get different accuracy because you're changing different data sets or maybe iterating through your data set one by one. But no, this doesn't change accuracy. It's just picking 100 from the test data set and testing those in the network. So yeah, that doesn't affect accuracy at all. It just tests more points to make sure you're not overfitting and whatnot. All right, so dataset directory, like I said, a lot of this code is just me doing stuff to help make this simple. You don't have to read it all. So this is the config part. So this is what you need to maybe modify. For the most part, you don't really have to modify this though, unless you really want to get into the simulator. So you got some bookkeeping with the paths. You have some tools, like if you want to skip the evaluation of the ANN, you can set this to false, and it will never even do inference on the ANN during during the SNN. You can set it to parse, normalize, or even simulate. No, to simulate or not to. So each of these things cost you more time in your inference. Not necessarily inference time, but it's just costing more to run it and simulate things on your end to do experiments. Okay. You specify the simulator, which is INI or any in this case. There's your duration parameter, how long to expose the images, how many to test, your batch size, and then your backend. So if you do PyTorch, you have to change this to PyTorch. So keep that in mind. So if you're, or no. Yeah, maybe you have to do that. I'm not sure, I don't remember. So if you're doing PyTorch, you may have to change that. Or you might just want to keep it off, like delete that entire line. Okay, and then you can choose what output you want. So by default, I have included these, and I'll kind of show you what these are and what they corresponded to. But these are what you're basically recording: the input image, the spike trains that come, I think, out of the network. The output spike trains, spike rates, spike counts. All of these are things that you can log about the spiking neural network's performance and behavior over time. And then, yeah, more options that you have, more other things. And then at the end, if you're using my code, I print what directory you're working in when you're running the code, as well as the data set and where the SNN is located. So if you want to grab the SNN, like you got a good model that you're really happy with, and how it's performing with the hyperparameters, the duration and whatnot, you can grab the model of it and back it up or something, take a copy. So, yeah. Maybe I'll run on Lambda and see if I can log into Lambda and do it. But yeah, I'll continue and show you the output. So those variables that I showed, the logging of variables, I've included this out directory. Oh, I didn't actually include the output, but inside that directory, you'll actually have a bunch of images and figures, and it will show you activations and stuff. And I've got some of those in the slideshow as well. But yeah, you'll get a ton of output. This is some sample output, and this is what you'll kind of get from the conversion toolbox. So you'll get your network architecture, the way it parsed it. So it tells you, just reiterates what you gave the network that you gave it to it. Tells you the parameters and whatnot. So this is just reading the network in. So I guess on this one I got predicted accuracy of 98. So it just tests those 100 samples that you chose at the beginning, tests them, and it looks at the accuracies. This is just testing the network you've already trained. No conversion yet. Now this is where things start getting a little bit more interesting. It parses the model, and it changes some activations around, whatnot. Gives you another kind of performance metric, shows you the network architecture and everything like that. And then it gets to normalization. So it says using 4,600 samples for normalization, that gets a chunk of the training data set, and then basically does some normalization computations. Like I said, that whole 99% percentile of activations, that's what this is doing. It's computing how much you need to normalize each layer or weights and whatnot. Then it scales the network up or down. Let's see, then it does a bunch of other stuff. And then before it's actually converted to spiking network, it gives you this kind of stuff with the normalized network. It gives you 76% accuracy. So now we get to the actual conversion part. So it builds the spiking convolution layers, compiles the spiking model, detects biases, whatnot, and so on. And it keeps giving you a bunch of accuracy. So this is where you start getting your training, or not training, inference information. So it saved the model, you start the simulation, and then it starts giving you the accuracies of your current batch. So here you have batch 1 of 3. So our batch size was 32, and we're testing 100 samples, so we should have 3 batches. So yeah, this is 3 epochs, or not 3 epochs, but 3 batches of inference. And it gives you 98%, and then, what does it say? I can't read. 96.8%. And then by the third chunk, it gives you 97%. And then at the end, it just averages all these together on, it says, hey, 97 total over the entire 100 samples, or 96 samples. If you notice that this also kind of gives you an idea of what these spike rates are. So this is another thing that you can enable and say, hey, I want to know the average spike rate of the network. So yeah, that's pretty much it. So back to this slide. So I kind of showed you this. I guess I should have gone over this slide first. Okay, so like I mentioned, there's an accuracy versus latency trade-off here. So that the longer or the higher that num steps per sample variable is, the more latency you're going to involve, because you're having to sit there and have a huge spike train injected into the network if you have a really high duration value or high num steps per sample. If you have a lower one, though, then you might not necessarily get good accuracy results. So you kind of have to tune in and maximize that, find an optimal point in there. Okay, higher batch size. This is especially true for this AnySim. The more the higher batch size, the more of the risk you run of running out of memory. So it explodes. I think actually I put a warning about this in the code. The higher batch size you use, it's going to chew up a crap ton of memory. I think I increased the batch size to, I think, 64 even, or I don't remember if it was on CPU or GPU, but I increased it to 64 or 128, and it was like using 40 gigs or something of memory. So be careful with your batch size. Don't go too high. And then, yeah, evaluation step performs inference on the ANN and SNN at the same time. So this is what the kind of figures I was talking about that it'll output. So you've got your input image, just a copy of what you're doing inference on. Then it records the spike trains. So you've got your neuron indexes. So this is the index of the neuron inside your network. And then the spike trains at each time step. So it kind of has a little bit of a pattern going on. And then the last layer. So you can see down here, it's very tiny. Actually, last semester I actually zoomed in. So if you look down here, this is your output layer, and you've got all those spikes on 0. So instead of doing softmax, you can actually just plot this, and you can see which neuron index 0 through 10, if you're on MNIST, which one spikes the most. And you can also see that 4 gets hit a little bit here, 2 gets spiked a little bit, 7 and 8. But for the most part, 0 is clearly the winner here. Okay. So back to presenting. There we go. And then you've got the activations of the layer. You can get certain activations to certain layers.
I just noticed something. So there was one metric in the. Yeah, that's good. So there's one metric in the conversion was done, and that was the top 5 accuracy. So how many of you know about this concept of top 10 accuracy? So top N accuracy is when your target output is within the 10 neurons that is selected. So if you have 10 classes, if you say top 5, it looks at the top 5 cases. What is top 5? You can see here. And see whether the targeted output, which in this case is 0, is selected in the top 5. Okay. But if you look at this guy here, this is something interesting. So the output is 0. Then we have some spikes in 2, some spikes at 8, and some in 4. So you can see we get spikes at 4 and 8. And if you think about it, one of the reasons that we are having some spikes at 4 and 8 is because we have 0. And then the 4 can be something like this. And then we have 8, right? So this is, and we're not very close, but these are closer to 0 than 1, for example. So that's why then you see, or 2 are also the same sort. So you can have 2 of this sort, right? So you get some spikes at 8 and significantly lower some of the spikes, but you don't get anything at 1, for example. 0 is very different from 1. And that's when the concept of top N comes to the picture. And sometimes we choose top 2, top 3. And that shows that your network might be good, but your input is very close anyways. And that's why we have some spikes here. Just notice the spikes at 8. So I was like, okay, that's cool to talk about it a bit.
Well,
Yeah.
I'm wondering what would be the difference, like what difference network could see between 1 and 7. You're not even human usually, right?
Oh, I think I actually ran this experiment, and it does this. It triggers on 7 and 1 quite often.
So one is very close at the second option.
I think in our paper, one of the papers that I did, it actually shows on the confusion matrix that 1 and 7 often get flipped around.
This example was 1. You probably would have seen a little bit more spikes than 7.
So, yep. So yeah, all of this output, now it doesn't do it for every single output. It just takes the last inference that you do, and that's what it gives you. So you might have to do some data set manipulation, like on your test data set when you're passing it through to make it the last image if you want to test a certain image. Because again, my code just randomly picks 100, so your ending like 100th image may be different each time. So if you want to make that static, you can just sort through the images and make sure that the last one is the image of digit that you want or test image. So yeah, this is provided to you. Like I said, in the code, you have that log vars or whatnot, or plotting flag. So maybe I should just go to it and show you. AI. Fine. So you have this plot vars. So this is what you can actually get rid of. You can get rid of these if you don't want to plot all the variables and worry about plotting all the time. This actually slows down your experiment significantly. Because if I were to show you this running, after each batch it plots all the results again. So plotting takes a good amount of time. So if you want to do your experiments fast and just log the variables, then there's also a logvar configuration as well that you can look at the toolbox simulation or the toolbox configuration for. That will just log them for you instead of plotting them every time. But yeah, plotting will slow down your experiment. So if you want to speed them up a little bit and do more experiments more often, then you can get rid of those a little bit. Okay, so I think that's almost it. So yeah, project 3 in this class. I guess is VGG9. I misspoke and said VGG11. But really, I mean, if you want to tinker around, the object of this is to learn how to create a neural network, first of all, and then convert it. So you can actually maybe, I don't know, Dr. Zan, do you want them to specifically do VGG9? Or could they maybe try other networks and see it? Yeah. Okay. We tested it.
Yeah. What to expect.
Yeah. So, but I mean, after you submit your assignment, if you want to tinker around for your like actual specific project, that's encouraged. You can tinker around with it more and whatnot. Just make sure to do VGG9 at the least for the assignment grade. So yeah, so you can do some analysis. I think part of this part of the homework, the project 3 homework, is actually kind of analyzing what's going on. So you'll look at those graphs and whatnot, maybe include some in your write-up that kind of analyze accuracy versus latency. So you can tweak that duration or num steps per sample variable and see that trade-off. You can kind of iterate over them, run multiple tests to see that, hey, it's got basically a line that goes steeply up and then it plateaus. So for longer durations, it plateaus with accuracy, but for lower durations, it's a steep kind of correlation. Okay, so I've included some helpful links. I don't know if Dr. Zan gave you the slides for this already.
No.
He'll post them.
It's going to be module 8 now. It used to be
Module 5, yeah.
Yeah, so we don't want to.
So yeah, we'll upload the slides so you can have access to these links. So you got your TensorFlow tutorials, and you have this is the toolbox. So if you want to figure out more configurations and tweak with them more, you'll go to this SNN Toolbox link. This is a source code if you want to dig through their source code and see how things are implemented. So if you go to GitHub with the Neuromorphic Processor project, that's where the SNN Toolbox actual source code is. Yeah, and they have some tutorials on there as well, so that can help you. And then this is the actual paper that goes along with the SNN Toolbox. So you can read it if you want to figure out more about it, what's going on under the hood. And then this is the class GitHub if you haven't seen it yet. So, yep, that's pretty much it.